Dear students and participants of the course on railway engineering, now we are going to start with another topic. This is related with traction and resistances. In the previous lecture, we discussed about ballast, the functions of the ballast, the requirements of the ballast cushion which is provided as a part of a track, the depth of that cushion, and there we have discussed about the minimum depths which needs to be provided under different conditions on the track. The specifications of the ballast were then discussed. Therein, we also talked about the oversize and undersized ballast and what are the cases where the ballast which has been received for the construction of the track can be rejected. Next to that, we discussed about the sampling techniques, and then finally we talked about the various types of the ballast which can be used on a track, and there we identified there are few cases which cannot be used on the main track completely or as a permanent way. They can be used temporarily, but after some time they have to be replaced by a better ballast. Now, in today's discussion, we are going to talk about traction, and then after traction we will be discussing about the resistances. Now, there are different type of resistances which are offered on track, but in today's lecture we will be taking up the rolling stock resistances and the resistances which have been caused by the gradient which is a part of the track profile or the alignment. Now, coming to the traction. Now, traction is what? That it is a source through which the locomotive gets driving power. So, our interest is the driving power. Whatever is the source which is there at the back end is a secondary concern, but when we talk about the sustainability issues, then you will say that there are certain things or certain types of the tractions which are coming, which have been used on the railways should not be used further. So, in that form, if we talk about the various sources, there can be three different sources. One is electric condition, another is diesel, and the third one is steam. The steam locomotives have been in use from the very starting on the railways, and that has been true for the Indian railways too. And slowly those steam locomotives, they were replaced by the diesel locomotives, and then as a new trend, when we are going for the electrification of our total network, wherein out of 68,000 around 50,000 has been already electrified, we are moving towards the electric traction and the electric locomotives. Now, if you look at the today's scenario on Indian railways, we still have 39 locomotives which are steam locomotives. That means they are using the power which is being generated by the steam, and then they propel or haul the train or the wagons which have been attached to that locomotive. We have 4747 locomotives of diesel, and if we talk about the broad gauge, the ineffective percent utilization is 9.79%. That means only this much are the locomotives which are not in use or they are not effectively used, but otherwise rest of the locomotives are in use and they have been used at one or the other part of the track throughout the country. Coming to the electric locomotives, we have 8,429 locomotives as of today for, and if we talk about the ineffective percent utilization, it is further lesser, it is 5.85% only for the broad gauge. So, that gives an idea that whatever locomotives we have, the Indian Railways is utilizing those locomotives to the maximum possible extent, so that none of the rolling stock remains in the yards or in the sheds without any use. Now, if we talk about electric, there is a possibility that the traction can come in terms of a alternate current or a direct current. So, it can be an AC or DC condition, and this 8429 locomotives, that is for both. Now, this traction or power which is coming through either the steam or the diesel or the electric condition, it has a bearing on majorly the first two conditions, that is the load carrying capacity, which is also being defined as hauling capacity, and that defines that how many wagons can be attached to a locomotive, and the locomotive will carry those wagons on a plain terrain or on slopes or on curves. So, whatever is the type of the track which has been provided. Another important issue is speed. The power which is available to a locomotive will define that at what particular speed it can operate. So, there can be a maximum speed and there can be a permissible value at which that locomotive has been utilized, or we can say that there is a operational speed. So, these two values are going to be there, and nowadays when we are talking about the high speed conditions, we are looking for 160 kilometers per hour or beyond 160 kilometers per hour. So, this particular selection of the power or the traction becomes important. Now, once we have talked about this, the other two criteria which can be there is economy and efficiency of service. Economy is in terms of the cost, and that cost can be of locomotive, it can be with respect to the fuel consumption, and it can be also with respect to the maintenance cost. So, all of these things needs to be looked at when we are talking about the economy associated here. And efficiency of services, that whether they are going to be delays because of any of the reasons, whether how much reliable is those type of locomotives to provide the services, and when they provide the services, those things being done within the given time frame. So, that type of efficiency, this efficiency can be talked in terms of time, it can be talked in terms of the efficiency of use of the resources, the fuels, it can be talked in terms of the turnaround conditions, it can also be in terms of the thermal efficiency. So, there are different factors which can further be associated with this. Now, when we have an idea that these are the points which needs to be considered, let us have a comparison across two of the locomotives which are still in use, that is electric locomotives and diesel locomotives. There are n number of points of comparisons, and we are going to look at all those points one by one. The very first one is the source of energy. From the name itself, when we take up, the electric locomotives will be getting the electricity as a source of energy, whereas in the case of diesel locomotives, it is on the basis of the diesel which comes out of the refineries. So, this diesel is already available as a one output and is being put as an input here, and electricity is being generated at some other location, and then it is being brought to the track by the use of the overhang conditions of wires through which it is finally taken to the location. Another case can be the engine design and weight. Now, if we talk about engine design and weight, the electric locomotive is a bit complex in design, but it is lightweight. It is lightweight because the power is not being generated on the locomotive itself, and due to that reason, the various types of equipments which otherwise could have been required, say if we talk about diesel, in the case of diesel it is being generated on the locomotive itself, and therefore there are different type of equipments which are being placed there, and that increases the weight of the diesel locomotive. So, here the electric locomotive is lightweight, but as far as design is concerned, internally it is a complex. Hauling capacity, that is how many wagons, how much load that locomotive can carry. So, electric locomotives are found to be better, and it is because the torque which is available with these electric locomotives is more steady in nature as compared to the maybe the diesel, or if we talk about the steam engine also here, so there is a much more problems in terms of that steady torque. So, again the electric locomotive has a upper hand here. The tractive effort available. Now, of course, there are different levels of tractive effort which are available in diesel as well as electric locomotives. If you remember, then we talked about the nomenclature of the locomotives, and there we said that it can be WAG. So, when we say WAG, W was for broad gauge, A was for electric traction, AC traction, and G was for goods. And there we also talked about the speed, we also talked about the axle load, and there we also talked about the overall weight. So, there are variety of such locomotives which are available, but as far as the overall comparative condition is there, we can say that electric locomotives has a relatively higher position here as compared to the diesel. Then speeds, because the tractive efforts are better available in the electric locomotives, therefore the higher speeds can also be achieved for the electric locomotives. The power utilization, is high in the electric locomotives because there is no wastage. In fact, in the case of a diesel engine also, or diesel locomotive also, the wastage is not there, subjective at the time when it is switched off. While when it is working, then there is some wastage, though that wastage is still not very high, but relatively if we talk about these two type of locomotives, then yes, there is a difference. The another point of comparison can be fuel consumption. Now, how much fuel is being consumed? Obviously, in the case of diesel locomotive, because the generation is there on the locomotive itself, therefore, there is a direct fuel consumption and is high. But if we talk about the electric locomotive, then nothing is being generated there, it is being taken to the locomotive through the wires. So, generation is somewhere else, and that is not being taken into the account in this particular case. So, some people can say that there is a diverse idea, there is a idea against this particular point, that the diesel locomotives are consuming more. If we account for the electricity generation, the picture may be different also or equal also. Another issue with the diesel locomotive when the fuel consumption is being talked is that it needs refueling after certain distance. So, there will be a station where this diesel locomotive will be filled again with the diesel, and then it will be moving forward. Shed requirements. The shed requirements in the case of diesel locomotive, quite variety of equipment may be required because the type of installations which are there, and therefore a typical or specific shed requirement will always be there in the case of diesel locomotive. But if you talk about an electric locomotive also, there will be requirement of some different type of equipments, on a number of equipments may be a bit lesser. Repair and renewables which are to be looked here. So, there is a less maintenance which is required on electric locomotives, again the reason being the type of equipment or the number of equipment which has been boarded on the locomotive itself, they are less. So, that from there it comes out to be a lesser maintenance requirement. The flexibility of use, diesel locomotive has been found to be more flexible under the varied weather conditions. So, here at this point the diesel locomotive has an upper hand as compared to the electric locomotive. The rate of acceleration, it is best in the case of electric locomotive, but as it is still a good in the case of diesel locomotive also. But because we are making a comparison, that is why this is best and that may be better. Then continuing with the points of comparisons, the cost is another point. The cost of locomotive, the electric locomotive is being observed to be costlier as compared to the diesel locomotive. The thermal efficiency in the case of electric locomotive is very high, it is around 90%, and this is because of the centralized system and because of the minimum emissions which are there. If we talk about the emissions are also less in the case of diesel locomotive too, but the thermal efficiency in the case of diesel locomotive as compared to the electric locomotive is quite low. Then pollution and hazard. Now, pollution and hazard, because no emissions are there in the case of electric locomotive, there is no noise which is being produced, whereas if you talk about the diesel locomotive, because the machinery is working there itself to generate the power. So, the noise is going to be there. There is no heat generated. Again, in the case of diesel locomotive, there is going to be heat. So, electric locomotive again is better on this count as compared to the diesel locomotive. And we can say that the electric locomotives as such are pollution free. Then slipping on or adhesion with the track. Now, slipping on or adhesion with the track is being defined in terms of the ratio of the tractive effort to the weight. Now, this ratio of tractive effort to the weight, if we talk in this particular form, it has been observed that more or less both of the locomotives, the diesel and the electric locomotives, comes at par with each other. So, we are not putting something like a best, better or a good type of a adverb here. Then life of locomotive, though more or less they have similar lives, but if you talk in terms of the economic life, that it provides your service at economical level, then in that particular case the electric locomotive has 30 years of economic life as compared to the 15 years of economic life of the diesel locomotive. So, this is also another important aspect, that when we are using electric locomotive, then it allows us to go ahead for at least 30 years, and then after only there will be a requirement of some changes or replacements. The next point here is the haulage. Now, relatively higher number of coaches can be attached to the electric locomotive because the tractive effort which is available to the electric locomotive is higher. So, it can just pull more number of wagons. The ratio of horsepower to weight, it is lower in the electric locomotives as compared to the diesel locomotives. The track riding, that means how you feel when you are being driven by a electric locomotive or a diesel locomotive. So, it's more smoother in the case of electric locomotive as compared to the diesel locomotive. And finally, if we talk about the suitability of the electric locomotive is there for heavy loads, for moving on the gradients, to achieve high speeds, to even work under the underground tracks. So, those suitabilities are there. But when you talk about the diesel locomotives, yes, these can also be used for the heavy load conditions, but then for the intermediate traction efforts. Or one thing which can we add here for the case of diesel locomotives is that it can be used in the varied weather conditions as we discussed previously. So, that is another side where some positive things comes for the diesel locomotive also. Now, let us come to the resistances to the traction. Now, these resistances to the tractions, they can be classified as resistances due to rolling stock, resistances due to track profile, then due to the tractive effort, and finally due to wind. So, there are 4 types of resistances which can be there. In the case of rolling stock, again we have resistances due to the parts where the speed independent conditions are there, they are not governed by the speed, or there are possibilities where they are governed by the speed. So, speed will become one of the parameter or an attribute in that particular calculation, and the third one is the atmospheric condition where we assume that the wind is not blowing. In the case of track profile, again we have one as a gradient and another one as curve. And if we talk about the tractive effort, then it can happen in terms of say the starting or the acceleration. So, these are the varied resistances which can be offered, and if these are being offered, then the locomotive has to counter these resistances so that it can take and haul the wagons or the train on that particular track. So, these two are correlated. So, we say that resistances are correlated with the hauling power, or we can say the hauling capacity. Now, let us start with these resistances. So, as we discussed, there are train resistances which are due to the rolling stock, there are resistances due to track profile, there are traction losses which are due to the starting or the acceleration of the locomotive on a track, and finally their wind resistances. We will be taking up these resistances one by one. In today's discussion, we will be able to complete the first two, that is the resistances which have been offered by the rolling stock and the resistances which are there due to the track profile. Now, when we talk about these resistances due to the rolling stock, if you go back, we can see that in the case of rolling stock, we talked about three: the speed independent, speed dependent, and atmosphere. And within speed independent, there are other cases like external friction, rolling friction, track resistance, and internal part friction. On the case of the speed dependent, what we have is a due to the track irregularities, due to vertical movements and flange action. So, these are various things which will be there. Starting with the resistance due to the rolling stock, independent of speed, dependent on speed, and the atmospheric resistances, as we just talked just now. So, starting here with the resistances which are independent of speeds, there were four such cases: the external resistances, the resistances due to track and all. So, here the first one is that there is a friction which is being imposed due to the train components. When we say train components, we are talking about the locomotives and wagons and their components. So, their components can be what? Their components can be the lubricants being used, type of bearings being used, and the temperature effects which can be there, which will heat up these type of components which have been used there, roller bearings, coupled boxes. So, all of these things, they also cause or they also create some resistances, and these resistances, they are known as external friction. Say in the case of a roller bearing, the resistance is 0.5 to 1 kg per ton. So, if the locomotive is going to haul 1000 tons, then you can understand that how much of the resistance is going to be there. So, it is 1000 tons means 1000 kg effect is going to be there, or 1 ton effect is going to be there. Similarly, in the case of coupled boxes, it is 1.3 to 1.5 kg per ton, and that too related, we are talking about a hard grease. Then there can be another friction which is between the steel wheels and the steel rails. So, continuously the wheels are moving at the top of the rails. So, that friction will also be there. The another one is the track resistance due to the wave action of rails. If you remember in the previous lectures, I talked about that if you have a rail being provided like this, and there is a wheel which is moving at the top of that with some speed v. So, there is going to be a deformation here. I can say this is a sort of a deflection which will get created because of the load which comes through this wheel on the rail system. And when this happens, it causes a bit raising effect of the rail at the front of it. And if this wheel comes to another location here, as it keeps moving, so again there will be this type of a deflection which will happen, but in between wave got created, and this wave gets moving along this rail section with the movement of the train or the wagons or the locomotives. So, that action which is there, this also poses resistances. And resistance can also be there due to the internal parts like cylinder and rim of the driving wheels and all those things. All of these resistances, they have been combined together and they have been written here as RT1, and this RT1 is equals to 0.0016 multiplied by W, where W is the weight of the train in tons. Now, if we talk about this weight of train in tons, say for an example, if there is a freight train which is of 42 BCN wagons, then this 42 BCN wagons, this will weigh 2560 tons. Just try to understand that how much weight it is going to carry. And if it is a box N wagon and there are 58 such wagons which have been provided, then it may be carrying a weight of 3828 tons. So, this is the amount of load which is being carried, and if we bring this load here as W, and multiplied with 0.0016, we get a substantial value in terms of the resistance which is being offered here. And this is independent of speed. This is only because of the locomotives and wagons and their weights and their couplings and their various other components. Now, just to give an idea that if say we are connecting 3 AC coaches, 4 AC coaches, and then within the AC coaches also they are different, or we are connecting the coaches which are of a second sleeper type and likewise, then in the case of AC chair car, it may have a 47.3 tons when it is loaded. AC first can have 43.5 tons of a load. AC 3 tire can have 48.8 tons of a load. AC 2 tire 46.72 tons. Pantry itself can also have a load of 48.2 tons. The second class can have 49.1 tons. The generation van can have 56.8 tons, and the locomotive itself can have a weight of maybe from 112 or 110 tons to 123 or even more. So, when you take all of these together, then you can very easily come up with the values. Now, here this is a train resistance independent of speed. All the things are being shown that Zernal resistance is there. So, here when you see A, this is Zernal resistance which is being caused due to the various components of locomotives or wagons. What you can see, this is a constant value. So, it has nothing to do with the speed. Whatever is the speed is there, it is constant. But when you talk about the flange resistance, which is defined here as B, this flange resistance starts increasing and the rate is not very high, it is just a mild slope. But if you talk about the air resistance, that air resistance is being governed by the square of the speed, and that is the reason we get this escalated value. So, you will find that it starts increasing at a very faster rate as soon as the speed starts increasing much more. So, if we talk about the lower speed spectrum, there the Zernal resistance is the highest one and it is causing the effect, but as you go ahead and you come to the higher speeds, then it shifts to the air resistance. Now, come to the dependent on speed. In the case of dependent on speeds, the problems can be with the train is moving at a speed. Now, why the resistances come? It can come because of the track irregularity. It can be there because of the vertical movement of wheels on the rails because of the improper joints or because the maintenance has been not done in the right manner, or it may also happen because of the flange action. And flange action, when we say it, is that the flange is moving in the one direction. So, the flange is there, so it keeps moving here in this form on the track. So, this because of that reason also there will be the effect, and it has been observed that the resistances, they are proportional to 1 by length, that is inversely proportional here of the resist base, or it is proportional to the speed of the train and square of that. So, the train resistance here, it is being defined as RT2, and the formula for that is 0.4 times 0.8 into W into V, where W again is the weight of the train in tons and V is the speed of the train in kilometers per hour. So, this is another formula. Now, if we talk about the speeds in the different locomotives, WAP 5 160, WAM 4 140, WAP 1, WAP 7 130, WA 4 this is 120, then WAG 6 again 120 in the case of goods. So, this was for passengers, this is WAP 4 and this is for goods. WAG 7 and 9 has 100 kilometers per hour speed, then WAG 9H has 90, 5A and B, 5HA, HB it has 80 kilometers per hour speed. So, accordingly you will find the resistances are also going to be varying. Here this graph shows that with the speed increase, as it is increasing here, what happens to the force which is there. So, tractive effort up to certain level, as you can see here, say roughly around of 20 meters per second, that remains constant, and after that it starts is reducing exponentially. Now, if you talk about the atmospheric effect, in the case of atmospheric effect, it acts what is happening is the atmosphere is everywhere. So, it is creating an impact on the ends as well as on the sides of the wagons and the locomotives. But we assume that the wind is not blowing, that the wind resistance is a separate resistance which we will be discussing. So, based on that, this RT3 has been computed, but it is being affected by the square of the speed, and it is given by 0.0000006 W into square of V multiplied by W multiplied by V square. Again, W and V have the same notations. So, finally, if we talk about the total train resistance RT, this is nothing but this is 0.0016 W plus 0.00008 W into V plus 0.0000006 W into square of V. Now, let us look at one of the numerical here. There is a train which weighs 1200 tons and runs at a speed of 80 kilometers per hour on a broad gauge track. We have to calculate the train resistance. Now, in this case, the train resistance RT1 is going to be with respect to the independent and dependent on speed. So, we and atmospheric conditions are the three such formula are there which are available to us, which we have just discussed. W is 1200 tons and the speed V is given as 80 kilometers per hour. So, if we put those values here, what we get is 1.92 tons of the independent condition, 7.68 for the speed dependent condition and 4.608 for the atmospheric condition, which together comes out to be 14.208 tons. So, this is the amount of resistance which is going to be there for this case. Now, there is another numerical which we are taking here. There is a train which carries 12 wagons and we are being given the classification of the wagons, that there are 1 AC 2 tire, 3 AC 3 tire and rest are the second sleeper coaches. Now, once this data is being given, then we have already seen that what are the values of the weights for these particular wagons. So, we will take those weights. So, if we take those weights, we will get some value here. So, we calculate the weight of the train. The weight of the train comes out to be 565.92 or 566 tons. This is on the basis of the weights of those wagons, and it is driven by a WAP7 locomotive which is having a weight of 120 tons. So, this is also added in this 565.92. Train is running at a speed of 110 kilometers per hour. So, that is given. So, again using the same formula which we have just discussed, and when we put the values here, what we get is 9.995 tons or roughly 10 tons of the resistance is there in this particular case. Now, let us talk about another resistance which is due to the track profile. In the case of track profile, we discussed that it can be because of the gradient, it can be because of the curvature. Now, here you can see that the gradient is being set. So, this is an angle theta at which the gradient is, the train is moving in this direction towards the up, and this gradient can be defined either by this angle, it can be defined as 1 in n or it can be defined as x%. There are different ways in which it can be done. Now, when we are talking about this resistance, now the weight is acting downwards. This is a normal force which is acting with respect to the surface and it is moving with attractive force in this particular form. So, the resultant Rg which is acting along the surface, but in the opposite direction, that Rg we are talking, and that Rg is W sin theta or W tan theta if the angle of this theta is very small. Usually for the train tracks it is very less, or it can also be written as W into the percent slope. So, this is how we can calculate the resistance due to the longitudinal gradient. So, just look at numerical on this. Track is being laid with a gradient of 1 in 200 and it is running on this section and experiences a resistance of 5.5 tons due to gradient. Gradient resistance is already being given, and what we have to calculate is the weight of the train that can be hauled on this gradient. So, we have a formula Rg is equals to W into percent slope. The percent slope can be found out because we have been given 1 in n. So, it is 1 in 200. So, 1 by 200 is the value. So, it is, and if you talk in percent, so it is multiplied by 100. So, 0.5 is 0.5% is the case. So, when we use that 0.5% here, so what we get is 0.005 into W, and because the resistance is being given to us as 5.5 tons, if we put it here, what we get as W is 1100 tons. That means if there is no other resistance being offered, only this thing is there, then in that case this locomotive can haul 1100 tons of the weight. So, we close now this lecture. What we discussed was the traction of locomotives, the associated factors, their comparisons, and then the resistances which are caused due to the rolling stocks and the track profile, and specifically the gradient. With this we close it. Thank you. We will meet in the next lecture.